Hello everyone, welcome back to the stream where we are making an emulator for the NES console in Godot. So last time we was following this rules tutorial, making sure that we have all the functionality working in place, and we made good progress up until now. As you have probably seen in my intro screen, we are about 3% the process. It is not much, but it will pile up. So, this is where we left. We was making sure that our addressing function was working properly. So now, in theory, we have all addressing modes working properly. We have not tested them yet, but that will be exactly the next step. So, as a reminder, immediate would use the content of the program counter as a literal value. Zero page means that it will use the content of program counter as the position in the first 255 slots of the memory. Absolute means it will read 2 of the bytes in the program counter, then use that as a memory counter of 2 bytes. Zero page X means it will read the program counter and then add the X value. And for the Y it's the same. Absolute X, it will read the value from program counter as 2 bytes and then add the X, and the same for absolute Y. And the indirect X and Y was the weird ones. And these are the ones that we will more probably have to check. But this was the last thing that we have been doing theoretically. So the next step would be this. Change the way our LDA implementation is working. So up until now, our LDA function is taking the register where we want to load and the value we want to load. Now we also, instead of the value, we want to receive the addressing mode. So LDA will get the addressing mode, instead of value, and value is gonna be an internal value. That will be the result of getting operand address with our addressing mode. So in theory, now instead of passing directly our parameter in here, we will choose, say, we want to read the value in addressing mode, and this part is going to move after, because we no longer get the param in this place. So let me check this. So yes, we have to get the operand for the address and then get the value. So In our load, we are going to get the address and then var value is gonna be memory memread address, and then we are going to set the register and update the flags just as before. So that means that now we can have all the load opcodes using this method. Let's check. So it's A9 for immediate, A5 for 0 page. Oops. This one is immediate. This one is 0 page. Next one is absolute. And this one takes 2 bytes for reading the location of the memory. And this the same way we have done these 3, there are plenty more in the reference of ALDA. Can we link to the reference? Let me see, where is the reference? I hope it's this one. Yep, let's go one step earlier, and this should be the instruction reference. Okay, there we go. So now we're going to find LDA, and let's see the other ones that we have not implemented. We have implemented A9, A9, A5, AD, but not B5. Let's fix that. Zero x B5 is gonna read the absolute with 0 page x, and it takes 2 bytes as well. And let's hide this. Full page hide it. So this button. And next is 0 page absolute is already done. Absolute x is BD. Absolute y is B9. Indirect x is A1. And indirect y is B1. So now let's take a closer look, making sure we have written all of them. So it's immediate, it takes 2 bytes, so we add only one. 0 page is A5, it takes 2 bytes, so we add one. The other one we have added earlier in here. Absolute is AD, and we add 2 bytes, 2 extra bytes. 0 page X is B5, and it takes only 1 byte besides the program counter, so there is an error in there. It should only add 1 here. BD, absolute X, this one, it's BD, and it takes 3 bytes, so we add only 2. Absolute Y is B9, and it takes 3 bytes, so we add 2. Indirect X, it's A1, but it takes 2 bytes, so we should only add 1. And indirect Y is B1, and it takes 2 bytes, so we should only add 1 here. This is very verbose, but we are going to fix that later. There is no need to have all of this in a huge match function. But yes, this should be working. Famous last word. So let's give it a try and see if test passes. Did not print anything. Okay, test passed. But we have only tested 0A9. We have not tested the rest. So let's write tests for the rest of the functions. So first of all, let's make a master function. Oops. Test LDA load data, and let's call this one in here. And now we are going to call all the tests for LDA inside this one. This is just to have a more clear creative function. So now we can have this. Let's bring a copy of our script just as a reminder. We already have A9. Let's route the rest. So we are going to decrease this. We can delete all the program counter lines. Now I can find this and replace it by an underscore, maybe? No, it doesn't work because you cannot write a tab in this in the search box. So let's just do it manually, I guess. So this is how I am going to do it. I am holding Alt and putting the caret on every line with a click. We'll press backspace, delete, 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 underscore. We'll move back and we'll write test. We'll also add test here. Now we have all the codes here. We can take this part the text and delete it. I'm going to use replace to delete it from all the lines. So now I can choose complete this. I will hold Ctrl and Shift and press down, so I can type in LDA, and now goes the name and then load data and finish it writing the function name. Now I can select everything, go to edit, and I can convert the case to lowercase, and that will convert everything that was uppercase to lowercase as we like in GdScript. Now what I am going to do is copy this, go below my other test function, will paste it, remove the indentation, hold Ctrl and Shift and start pressing down. I can type monk, paste, go to the end, semicolon, new line, pass. So yep, now we have definitions for all our functions. We have to start making them work, right? So let's copy the first test, let's paste it, and let's start changing it to make our tests as we want. So the instruction is now A5 and not A9. And as we can see, this is the 0 page load. So this is the first 155 memory slots. So what we are going to do is use LDA to store a value in the first location. Wait, can we store? Let's just do this. Load and run, load, rested run, and rested will reset the memory, right? Oh no, it does not reset the memory, so we can't set the memory beforehand. We can say CPU dot memory dot write, and in the address 0x10 we want to store the value 0x15 maybe. So now I want to load the memory from 0x, and the value should be equal to 0x15. It is 0, no. It is negative, no. Next, let's set the memory to, actually we can populate many values in here, 0x10 to 0x11, 0x12, and let's set this value in here, and we set this value in here. So for the first test we load x10, for the second test we load x11, a5, and for the third test we are going to read x12 with a5 as well. So now in the second test it should be reading this value and testing if it is negative, so it is not 0 and it is negative. That should pass. When reading the last value, it should be 0. So this comparison should match. 0 is true, negative is false. If this is correct, then A5 LDA 0 page load data pass. Let's try that out. Yes, it's passing. Let's go to the next one. And now we want to test AD with absolute value. That means we are going to read 2 bytes of memory and get the value from the second byte. So let's start writing some memory for reading values. So in this case we are going to read 0, 1, 10, 0, 1, 11 and 0, 1, 12. Okay, so the test will mostly match, but the only difference is that we are going to reference these addresses. Actually, maybe I should copy this other test instead. There we go. So now this one is 0x0002. And we are going to read from this other memory these other 3 values and make the same comparisons as before. But when we read first this is little endian, so we read first the last 2 bytes and then the first 2 bytes. So after this 10, 11 and 12 we are going to add the 0x01 second part of the byte. Let's see if this test passes now, because we should be reading the same values from a different memory location, and the passes should match and do exactly the same. So let's go. And absolute load passed. That's great. Now is 0 page x, that is, it reads from 0 and adds x to whatever it is. So what we are going to do is copy this one, because it's the version that takes only 1 byte. In this test, instead of 0, 1, 2, we are going to store the values on 10, 11 and 12, but we are going to pass 0, 0, 0, 1 and 0, 2 to the 0x5, right? So before we do this, we have to set the value of x. So we are going to use first A9, which, if you remember, is load in a constant. Is this one, load in a constant, and we are going to load a value of 10, and then we want to transfer the value of A to register X. So the function to do that is tax, is 0xAA. 0xAA. And then the rest of the function should be the same. And let's see if this function passes now. Let's go! And it passes! Wow, I am impressed myself. Can't believe this is working so nice. So next one is load absolute X. So it is this test but using absolute memory, that is 2 bytes. So I will copy the other version, the one that takes 2 bytes, and will paste it, and will change it in the same way. First of all, let's change what is the code of the function, and let's see what should we change. So first of all, we want to pass 0 here instead of a 1, and secondly, we want to also add the first part that loads the value into the memory. But we are going to store in the second page. No, actually that doesn't matter. Because this is the offset, not the full memory. So all we have to do is store the offset into the X register, and then we can theoretically test and pass the test. Okay, it failed. What I am doing wrong? BD is loading the register with absolute X. Absolute X is trying to get the operand address. It is trying to read an unsigned 16 from program counter, but program counter is a garbage value from what I see. Why did that happen? Let's go one step at a time. Let's stop and rerun. And now we can try to see what is happening in here. Okay. Is this correct? It's PD 0. Okay. So I suppose the program counter is not so wrong because it starts in 8000. And that is in hex, of course. Let's get in. It will load the program, reset, and run. We have memory, and let's start reading the opcode. We are going to set the value of 10 into register A, we are going to transfer from register A to register X. There we go. We are going to enter the, was it AD? No, BD. And we want to enter the register mode. So we want to get the operand address for absolute X, and when we do this, we want to get the base reading 16 bytes of memory from the program counter. We will enter. There is no function memread U16. Right, it is just 16. And why is it complaining it doesn't exist? Memread 16, memwrite 16, and it is complaining I am passing a register and not a value. Okay, that looks much better now. Do we have any other mistake like that? Seems like not. So let's try it again and see if it passes. It executed and no errors. So yay, it passes. We have absolute X working as well. This is why it's important to make tests, so you find it earlier rather than later. So what is next? Next is absolute Y. So let's take the same test from absolute X, and we have to change it a little. First we want to transfer to Y instead of X. Did we implement transfer to Y? Yes, we did. It is A8 instead of A8. So it is gonna be A8 for the sake of keeping everything consistent, we change that to lowercase. And now we are loading the same memory in the same location. We are loading the 10 offset into the A register, transfer it to the Y register, and then we are use absolute Y instead of absolute X. And see if this passes. Let's hope so. And indeed it is passing. Awesome. So what we are not yet testing is the warp. So the warp in the increment. But I think we can ignore it for now and add that case later. So next case is indirect X and indirect Y. And how is indirect X work? Let's try to understand it for making a good test. So first I will copy the absolute X just as a reference. Let's comment it for now until we know it works. And let's remember what the indirect X does. So indirect X reads the value, adds X, and then from that value reads the value. So, okay, it is going to read to read 1 byte from what I see. Let's confirm that. Yes, it reads only 1 byte. And it uses A1. It will read 1 byte. It will add X. And then it will read 2 bytes from that location. And it will use that as address for the next value. So this is complex. So first of all, let's change the command to use A1 instead. And this one uses only 1 byte, so we can remove one of these. We will probably remove the second one because it's the one that is the same for both. So our pointers are 0, 0, 0, 1, and 0, 2. So we can actually use some stuff here. So what we want is read from 0, 0, 0, 1, and 0, 2. Let's see, when we read, we are going to get, remember, we are going to get a single value and we are going to add X. X will be 10 as before. And that will become a pointer to read the next 2 values. So that means we want to read 10, 11, 12, and then it's going to point to this. Zero, 0, 0, 1, and 0, 2. Wait, is this correct? We add 10. Okay, so it's 10, 12, and 14. And this is 1, 0, 2, and 0, 4. This is because 10 needs to store this 10. Oops. 10 needs to store this 10. And 11 needs to store this 01. Because of little endianness. Now, for the 12, we want to have 11 and in 13, 0, 1, just like before. This will become 0, 1 from here and 11 from here. And for 40, we want 0, 12 and 15, 0, 1. Assuming I am understanding correctly what this function does. So we load register A with an X, we transfer it to X. What was this one? Transfer to X? XAA? Yes, transfers to X. And then we want to make the indirect load X load using A1, passing memory 0, which is this one, passing memory 1, which is this one, and passing memory 2, which is this one. Let's see if I am crazy. If I am correct, all these tests should pass. And I think I have to rename this, print, and see if this passes. And assertion failed in the second one. So this one passed it, this one didn't. And let's find out why. What is on register A? The value is 0. Let's find out what I did wrong. Relaunch. Let's enter this function. And let's see how it runs. So first, load a 10 in register A. Second, transfer from register A to X. There we go. Then make the indirect X access. There we go. We're going to enter and get the operand. Addressing mode should be indirect X. And then it will read one value from the program counter, which should be 0, oh sorry, 1. And we are going to add X, which should be 10, and get 11 here. Pointer is 17, right? Because it's on hexadecimal, so 11 in base 10 is 0, 1 in base 16. No, wait. No, it's 1, 0. No, it's 0, 1. It's correct. No, what? So low memory and high memory, 11 and 18. Is that correct? So what is 11? So let's go to the calculator. There is no need to make method things. Let's go to the programmer calculator and let's put a 17 in here. And we see that it is an 11. So it is reading indeed 11, and 18 is indeed reading the 12. So this one should be 0, 1, and 11 in the low and high. So let's confirm that. So Low and high are 0, 1 and 1, 0. No, is this correct? I should be reading this one. And this one should be this one. So something seems wrong here. I am getting confused. Give me a second. With the program counter, if we have read the value from the program counter into base, and it is 1. 1 is indeed this one, and we are adding 10 to that one. Okay, so I have read this one. Okay, I see what I did wrong. Did I see what I did wrong? So I get the value, add 10, and that's my pointer. This program counter value. I am a little confused. This one I read 0. I could have written that function wrong. Let's take a look again to how indirect x works. Wait, it was... I am in the wrong page. Indirect x reads the memory, adds x, and then gets the 2 bytes and applies it. So this is what I am doing, right? I am reading the memory, adding x, and use this as the pointer for reading the high and low values. So I am doing the right thing, which means I am writing the wrong test. So I read what is in the program counter. I should be reading 0 here, and here I should be reading 1. Memory. Let's go to run this again. So now program counter value is program counter value is 3272. And when I read the memory, my base is 0. So my pointer is 0 plus the value of x, which should be 10. Oh, right, it's 17, not 10. And pointer 1 is that plus 1. So low and high are these values, 16 and 1. I get the value and it's at 21. And we have passed the first part because we have been reading this part. So let's continue with the second test. Now I have another value in my program counter. And when I read the base, it is a 1, which is indeed what I passed in here. Okay, so this is not what I thought it would be like. So it's not even using this at all, is it? It is not using this at all. You just pass the 0 here, the 2 here, and the 4 here. It was not so indirect. What I wrote here is the other one, the one for y. So I will copy this and keep it for later. We'll comment it because this is how y works, indirect y works, and this is how indirect x works. So let's give it a try. So it's 0, 2, and 4. Let's give it a second try. Yeah, let's remove the breakpoint and continue. And seems like it indeed passed the indirect x. Now let's go to the indirect y. So let's make some fixes to my code. So now this one will have 0, 1, and 2. And this one needs to transfer to y instead of x. So transfer y was A8. A8. And we are loading 10, transferring to y, and then we are going to run this command, passing the memory of 0, 1, and 2. And let's see if this test now passes. Because what should happen is it reads the value, then reads the value from the value, and then adds y, and then reads the value. Let's see if that's true. Nope, that's not true. And what is register A? It is a 0 again. So I may have mistaken again. So let's check what is indirect A, y, and see if I got it wrong again. Oh, I see. I see. So no, it is not what I thought. It also does not use these ones. It will read the value. Let's check. It reads the value and immediately gets the value from it. Wait a second. I am not that crazy. Let's see what I am doing wrong here. So it gets the value base. And base should be 0, right? Yes. So the low value is base and high value is base plus 1. And then we have 0 and 2. Okay, I see, I see. So this one are the ones I am reading. So I am reading the 2 bytes directly from my byte argument. So this is 0, this is 02, and this is 04 again. But now I am reading the 2 values from here, adding 10 later, and that is giving me this value in theory. So it's 1001. So that also means that I need to subtract them from here, because it will be added from the register Y. So let's try again. Okay. Base is 0, low is 0, and high is 1. Tref is 272. Maybe correct? Wow, indirect Y passed. Awesome. So yes, we have all the tests for LDA working. Awesome. Hey, Els, how are you? God, the stream isn't loading very well for me. Oh, that's bad. I I don't know where to see if I have framing drops. Um, how are you doing? I am not used to looking at the chat, so maybe you have targeted me long ago. I don't know. So let's add another test for transfer to Y. Transfer to Y is A8. Move A to Y. Now it is gonna be A8 instead of this. And we are going to test register Y instead. And we are going to add this test to the top. Does it pass? It passes. Yeah. Let's see why the music stopped. There it goes. We have all the LDA functions working and ready to go, and with it we have also tested most of the addressing modes. Let's continue with our tutorial for now. Now, it is absolutely necessary to increment program counter after each byte being read from the instruction stream. Don't forget your tests. Load LDA from memory. I have done a new test for it. Using the same foundation, we can quickly implement STA instruction, which copies the value from register A to memory. Let's try to make it work in our way. So let's make STA func store or set or save, and let's go with store. That makes more sense to me. From register. So we are going to pass the register as before, and we are going to pass address mode. Let's make some conversions from Rust to GdScript. This is a variable for the address. We're getting the address from the addressing mode, and we are going to write on memory into the address and setting the value of A. Oh, it's per register. And this is a register 8 bits. Memory, not memory. I will have to try again on my PC. I can get this stream on my phone. Oh, that's so sad. I hope it is not a problem from my side. I don't know how to check statics to see if something is working bad. Studio mode, themes, App Store, highlighter, dashboard, settings. Yeah, I don't have a quality or anything. So we have STA working. We have to add the the cost of SPA. So let's go back to our reference and find SPA. Store accumulator. Okay, so it was a store, not set. We can do that. We can rename it to store. Store from register. So it does not affect any flag because it is only reading. So we don't need to test any flag change. And we have all these variants to address. So let's try to make them work. Wow, I don't like that. So let's try 85, and 85 is 0 page. 95 is 0 page X. 8D is absolute. Nine D is absolute X. $99 is absolute Y. $81 is indirect X. And 91 is indirect Y. 91. Okay, so let's get started. So we store from register. We want to store from register A using addressing mode, and then each one will have a different addressing mode. This one is 0 page, 0x, absolute, absolute X, absolute Y, indirect X. So this is indirect Y. Let's see. I can now delete these comments. Now we still have to increase the program counter by the right value, right? With program counter dot value plus equal, and let's start with a 1 and see which one is which. 0 page takes 2 bytes, so it's a 1. Page 8, 1. Absolute. The 3 versions of absolute should be adding 2. And the 2 indirect ones should be adding 1. let's take a look. Now we have to test this, right? We're going to test. So the good thing is we don't care about the flags, so we can just make only one test per SDA. Func test SDA store data. Pass. And we are going to test store right after testing load. So let's start with our command, our functions. We are going to remove the command argument. This is SDA, and instead of load we are going to store. Yay, we have almost the function names for our tests. Now let's bring what are the codes for them. Store starts with 85, 95. I think I can get it from the web. I will move this to my other desktop for a moment and check this. So immediate does not exist. Zero page is 85. Absolute is 8D. Zero page X set. Now X is 95. Absolute X is 9D. Lowercase d. And absolute Y is 99. Indirect X is 81. And indirect Y is 91. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, awesome. So just as before, let's move this after all the LDA functions. Yep, about here. Paste. Move indent. Func colon pass. And let's take the example from load, which is the simpler one. So in this case, we are going to check if memory read of value 10 is equals to 0.5. So let's make our function for that. We're going to load 0.5 into register A, and then we are going to store this into memory slot 0x10. Let's see, does this function passes? Here we go. Wow, it passed. We are storing the memory There we go. Copy, paste. Now it's absolute. It takes 2 bytes for the memory. So we are going to read from 1010 maybe. Now 1012. So instead of 85, we are going to use 8D, and we are going to pass first the 12 and then the 10 because of little endianness. And let's see if this function passes. Indeed, it passed. Woohoo! Okay, 0 page X. Here is where it becomes a little weird. We are going to add 5 into A, store it, and then also transfer it to the X register, which was the command 0x88. So we load a 5, store it in memory. Wait, did I do something wrong? Right, I should store it in memory. Sorry, before storing it in memory, I need to transfer it to register X and then store it into memory 1210. But instead of 12, I need 5 less because it will take the offset from, or I can read 5 more here, so it is 17, and it should read from 1017 05. So is this correct? Wow, it is. So, moving on. So we are going to store we load a 5, move it to register X, we store it 9D, wait, I think I did something wrong. This one should be the test of the non-zero page, because this is absolute, it takes 2 bytes. This is not absolute, this is 0 page, so this should be 17, and this bit should not exist at all. That was weird. Why did it pass? I don't know. Version failed. So zero page X still passes. So this still passes. This one is not passing. And this is because I am passing 17 here instead of 12, and it will add the 5 later. and now it passes with absolute Y. This is weird. So this is not 0 page 8. I load a file, transfers to X, and I should be loading. Oh, right. So it was still using the absolute. Okay, so 0.95, and this one should be 12, and it will add 5 and get into 17. Does it work? Yes, both works. 0 page X and absolute X, both works. Now absolute Y is pretty much the same, but instead of transferring to X, we are going to transfer into Y, which is A8. Instead of 90, we are going to use 99, and I am reading 12 plus 5, but it's just at 10, and this should be exactly the same, right? Does it work? It works. Wow. Okay, so here is where it becomes complicated. The indirect ones are harder. So, indirect X, let's take a look again. We'll get the memory and use that, add 10 and use that as a pointer. So it will load the memory, transfer it to X, and then it will be using 5 plus 5, it will be at 10. Give me a second, I need to think it, because indirect X ends up with a non-first page, unless I pass a 0 in here, so it will be on the first page, and 12 plus 5 will be 16, and it will be stored in here, 30, right? Right. And file. Let's see what is in memory. So we have 5 in the 0 memory. Is that correct? And transfer, and then store. Right. So this is the value I am storing, not the value I am getting. Where is my value? Okay, I'm doing it totally wrong. So let's think again. We loaded a 5 and stored it into X. That's okay, that's something we want. Now, for indirect X, store data into indirect X. Let's go back to this. Indirect X will read the value from the program counter, add X, and use that value on the next one as the argument. So it will get this 12. Yes, this one is indirect X, so it takes only one. Wait, takes only one? Does, right? Indirect X. Or indirect X, yes, only one. Okay, so what I want to do is storing this 5 somewhere else. So let's store 0 page is 95. No, not 0 page, absolute D. So after transferring, let's store this value into one memory location. Let's say 10. So we are going to store 5 into cell 10. And then we are going to oh, I am writing in the wrong line. So we are going to store in the 10 cell, and then we are going to X indirect read from it first adds, then checks the pointer. Yes, it first adds, then check the pointer. So I want 0x5. So it will be 5 plus 5, it will end in line 10. And that will make there is a 05 in line 10 and 00 in cell 6, 11, and it will be a 00. So I want to load at 3 and store in memory 0, 0, 0, 1. No, it's 0, 0. Is that correct? And that means the page 0, 0 should be 3. And loading at 3 and store SPA absolute is 8D in 0, 0. Okay, then of course it is going to be 0, 0. So what I want to check is if 0300 is 05. Close, I hope. Let's check my memory. So this is not looking good. So I loaded 3 in the register and stored it into 00, 0. Actually I don't need to do this the hard way. I can choose making it like this, right? So I am loading a file, transfer to X, and then using this one, transfers. Yeah, I don't need to do this. 8105. So it is going to take 05 and 06. Actually it's 10 because it is going to add the other 5. Then an 11, and it will find 03 or 0. Now then write 4003 and I am okay. This is the memory I want to check. Actually, I don't need anything here. Is this all enough? You want passes? No. Let's take a look at my memory. 16, which is 10, is 03. 11 is 40, 64. Looks correct. So we loaded a file, transfer to X, and then try to store the value of register A, I think, and we passed 5 plus 5, it will be 10, and then it takes 3 for lower, 40 for higher, and it should store the value of A, which is 0.5. I think this should work. Famous last words. So let's take a look to our callback in here. Let's try to make it work again. We must register A with indirect X. Get operand. Indirect X. It will read the program counter, and we have a 5. We are going to add the 5 from the register X. This should be a 10, and 11 should be the other one. Oh, and it is reading from that value. So this one could be 0x12 and 0x40. Wait. What I am doing? Then this is correct. 10 and 11, and I am going to read. This is correct. I'm going to read 03 and 40. 03. What? It's a 0. Why is it a 0? Pointer 10. Memory 10 is indeed a 0. Okay, nice. So it's 05 plus 05 10. I see. So I mistaken the base of the functions. So in order for this to reach a 10, I need a here, right? B, C, D, E, F. Actually a B. we add 5 C, D, E, F, and then it becomes 1, 0. Let's give it another try. Continue, and it passed it. Yes. Indirect X passed it. Wow, that was hard. So this one adds X and then reads the value. This one will read the value and then add Y. Let's change 81, 91, and let's try to make it read the same value. So I needed to subtract. No, actually, we can just add 5 to this. And this should work. Famous last word. Let's check it. Okay, so let's go with loads register X with 0.5, transfer it to Y instead of X. So I want to transfer to Y, which is 8. And we transfer to Y, and I want to use indirect Y loading with the same memory as before. And that means I want to read 10 directly. It will read 10 and 11, which will give me the address of 4003, and then I will add 5 and will get 4008, and it should be the value that I am expecting. And indirect Y passed it. Wow. I am very impressed. Wow, there is a lot of math involved, and it's very, very tiring, but it's going nice. So we have added STA. Before we wrap up, I'd like to mention that the current run method is somewhat iffy for a few reasons. First, we require to increment the program counter by 1 or by 2 after some of the operations, and this is error prone. If we made an error, we would be thought spotted. Second, wouldn't it be more readable and convenient if we could group all the LDA operations under a single match statement? Lastly, all we do is hard code the instruction spec into root code. The translation is a bit hard to compare. Keeping the code in some table form looks like more manageable approach. So yeah, so it is now creating a table, or better said, an array of opcodes, which is just some object that stores some values. And opcode, I think it comes from a built-in from an existing package that is being included into Rust. So it's not a class that it has written. I think we can check the entire sources for this in GitHub. So if we take a look, we see that he's using great opcodes. It seems like it is right that it is using an external package for it. We could maybe confirm it with cargo. Lazy static. I don't know. Maybe this. Maybe it's not. Bruce, lazy static. And what are you? doesn't seem to be related to opcode. Let's check if the opcode is written in here. Okay, so yes, he did his own opcode class. So I guess I will do the same. Yeah. I will start by making the same class, and I will put it in my interface. Use script opcode inherit ref counted create. Class name opcode so let's see what are the variables that they are using. I will move this to my other monitor so I can read it. Var code, and it's an integer. Var mnemonic, which is an integer. Oh, I should not have indentation. So let's have default values. Right, mnemonic is a string. Actually a string name, I guess. Because it's the legible name in assembler for the instruction. We have a len or size. This one says len. I prefer to have size because it matches the convenience of GdScript. Cycles, I don't know if they will be used in the future, but it is so many CPU cycles it uses to execute the function. And address mode, I will use integer instead of an addressing mode. But when I call this function, I will pass. I will cast it from the num. So now I want the initialization function. Actually, I also want a callback. For the execution. So then it will have all of the same. With a P in the start. So this one is an integer. This one is a string name. Size is an integer. Cycles is an integer. Addressing mode is an integer. And callback is a callable. So now I want to say each one of these is equal to p underscore and then each one of the variables. So we can create opcodes easily with the new function. So let's see how this works for the CPU. So we are going to have a bar instructions or instruction set. It's going to be a dictionary, and we are create the break instruction. Opcode.new. The code is 00. Let's see, what was it? Mnemonic is PRK. The size is 1. Cycles should be 1, I guess. I am not even sure if it exists. Addressing mode. It's just past a 0, which is for our NES CPU. Immediate. We don't care because it does not even has a next statement. Sorry, the size includes itself. Yes, it's fine. And is it the callable now, right? Sorry, I am a little confused. Yes, the callable. Oh, let's go quit. So, quit. So this one will be with boolean equals false, and quit will set quit equals true. So that makes that in our run function while quit equals false. Let's maybe use something different. Let's say is running instead, and we said is running to pause when you quit. So in run, we said is running equals true, and we do the same for our next game. And while is running, we will keep executing stuff. So now we have a function that can stop the execution. And I suppose rested should also set this running to pause. Yes. Do we have something in this reset function? No. I could add it as a reminder, yes. Registers, flag, program counter. Okay, this seems right up until now. So now that we have done this, we can actually register our instructions. So we are going to say instructions set, and let's start with the LDA section. Let's move this here for a moment. So we can take this one. Is equals to a new opcode. It's the same code with LDA with this addressing mode. I am following the right order of arguments. No, it's size first. So size is 2 for this one. 1 for this and 1 for the parameter. Then comes the cycles. And cycles, I have to read them from my documentation. I search for LDA, and for immediate cycles takes 2. I will move this to my other monitor to have a peek. Two cycles is the correct. Yes, cycles, address mode, and carbon. And the callback is going to be load register bin, and then I am going to bin register A and the addressing mode. Actually, this way I don't even need the addressing mode as part of the opcode, right? I think so, yes, because I will not use it. I will not even use cycles for now, but maybe the tutorial uses it later for something else. So yes, for now I will keep it this way. I will remove address mode. And now that I don't have address mode, the break function has an extra argument that I don't need. Here we go. Okay, so this is it, right? Now I have to start populating this mode with the rest of the instruction set. So let's copy this a couple times. Continue with A5. We'll read A5, A5, and we'll use 0 page. Done with this one. AD, AD, and uses absolute. I will fix the cycles and bytes later. Done with ID. 5, ID, D9, D5, D5. And 0 page X. DD, DD, 0 page X. P9, P9, absolute Y. Wait, what? DD is absolute X, sorry. Illusion of Gaia music. So awesome. Okay, so two more. A1 and B1. And this is indirect X and indirect Y. And this looks more or less like the table from the documentation. And let's see. compare it, shall we? So it has LDA for A9, A5, A5. Yes, the thing is they are using a vector. So I suppose I can also use a vector and then add them. Bar instructions, array of opcode equals to a new array, and then start populating it like this. It's like it happens in the other case. Let's make this fast. So we have all the LDA functions pretty fast, and we can just add more below this one. So let's take a quick look and compare our table with the documentation. Hide this, move this around here. We can now compare A9, ATA, Choo-Choo, immediate, A5, LDA, Choo-Choo, no, Choo-3, 0 page. AD is this one, inverted, and it's a 3-4, and it's absolute. B5, this one is 2-4, and it's 0 page X. BD is 3-4. Absolute X, LDA, sorry, B9, LDA 3-4, absolute Y, A1 is LDA 2-6, indirect X, and LDA is 2-5, and indirect Y. So yes, we got all the LDA instructions. So we have to keep doing the same for the SDA functions. Now we are going to get all the store from register And let's start changing this. So first, let's remove all the increments in the program counter. So let's start by, I want to change the function name. Oops. And the bins are theoretically the same. We don't have immediate. We have 0 page. Absolute is before 0 page X. Absolute X, absolute Y, indirect X, indirect Y. Okay, so these codes should be on the same order in here. And these names should be now SDA. Which, by the way, it should be a string name, not a string. Same here. Let's take a look. Yes, no new messages. Awesome. So now we have the SDA commands. We have to check the cycles and bytes, but the rest should be correct. Famous last words. So I will open our reference and search for SDA store accumulator, and here we go. We can move this over here, and we can start creating our populating our table. So 0 page takes 2 bytes and 3 cycles. Absolute takes 3 bytes and 4 cycles. 0 page X takes 2 bytes and 4 cycles. That is correct. Absolute X takes 3 bytes and 5 cycles. Absolute Y takes 3 bytes and 5 cycles as well. Indirect X takes 2 bytes and 6 cycles. And indirect Y takes 2 bytes and 6 cycles. Save. There is some error somewhere? No, there is not. This is all. Okay, so we have SDA now. And we can easily turn this into SDX, if I am not wrong. It is SDX, no flags affected, and it has only 3 implementations: 0 page, 0 page Y, and absolute, and the rest goes away. 0 page is 86. 0 page Y is 95. And absolute is 90. Sorry, 8E. Zero page takes 2 bytes, 3 cycles. Absolute takes 3 bytes, 4 cycles. Zero page Y takes 2 bytes, 4 cycles. It is correct, so the only missing part is changing register A to register X. And taking a look, STY is pretty much same. So let's take a look. Zero page X instead of Y, and absolute. So we can take this one, change it to XDY, change 0 page Y for X, changing the register from X to Y, and oh right, so this is SDX and this is XDY, and this is 0 page is 84, absolute is 8C, and 0 page X is 94. Okay, awesome. So we have all the store commands implemented in this instruction set. So now comes the transfer. So we have load, store, and transfer and increment. So let's see. Next is transfer tax. Addressing mode says it is implied. What does that mean? Okay, it means it doesn't need any addressing mode at all, right? Let's copy any line, say this is AA, it is called tax, and the function is transfer. Let's just copy the name, right? Transfer register from to, and this one copies from X to Y. It's from to from A to X. Yes, from A to X. This one goes from A to register X. So die should be very much the same. And is A8. Name it die. And transfer register from to, and this one transfer from A to Y. STX, sorry, TSX we have not done. The one that we have done is increment register. So it inc X in X and in Y. So let's find it. In X, increment X register. It is a unique function. Opcode is E8. Aim is in X. Let's comment it. Let's find the function. I don't want to a typo accidentally. Increment register, and we should pass one register for the one we want to increment. Correct. So now we can do the same for increment Y. Increment Y. Increment Y. Opcode is C8. Oh, I have forgotten to check this stuff. Takes 2 cycles. Takes 2 cycles. What about tax and die? It was 1 byte, 2 cycles, 1 byte, 2 cycles. Okay, sorry about that. So this should be all for now. So now I have a node in this vector to store everything, and what I am going to do is iterate all the instructions. For instruction, in instructions, instruction set to instruction.code equals instruction. So I had a vector, now I have a dictionary with all the instructions sorted by code, so I can more easily find it just with the hex code. So what goes next? So this one should go away. I should be able to do all of this without a match operation right now. So if sorry, let's better do par instruction, which is an opcode, equals instruction set the dot get opcode, and the default will be null, and I want to assert instruction unknown instruction with code code. How do I format this as hex value? And let's take a look. I am not that great for this kind. So let's see. Python format int as hex. Is it? Is it? Really? I don't think so. This is... I maybe in Rust. I don't think so. Will it be like this? Anyway, so with the instruction we can run the callable. Instruction callable is valid. Why it cannot compile? I am setting the type. Well, whatever. Let's try to test it. Instruction callable call and program counter dot value plus equals instruction dot size -1. The reason I say size -1 is because I already advanced one after reading the opcode. This should theoretically already be working with our instruction set table. Let's give it a try and see if test passes. Nope, it failed. Okay, let's give it a try. So it failed with the very first test. The register A of CPU is 0. So let's see what is it doing when we run and load this load register function. Launch it, and we are apparently not running the function at all. So let's go to our run function and see what is happening here. Right, while is running is true, not false. We got an unknown instruction. The code is 169. 169 is the hex A9. A9 should be this one. So why is it not in the table? What is our instruction set? Let's check. Instruction set. We have 25. 169. We have an 169. Why did we not get it loaded into instruction? Okay, that was weird. Seems like, oh, okay, so unsupported. So it was an error in the print, not an assertion. So it did not like our print. But it gets installable. What is it called then? Oh, callback, not callable. Okay. Callback. Let's go again. Okay, it entered the function. This register is probably register A. Let's continue. Okay, increment X overflow failed. And why is that? Let's see, what is my CPU? Register X is 4 and register Y is 255. So let's see what this register is doing. First of all, we have registered properly the increment X. Oh, I see. We passed the same argument to increment Y. Okay, everything passed. Yay! We did it! Okay, so I think we are done with this chapter, right? So next is move on. How to try? Oh no! Draw some circle, draw the rest of the owl. Okay, this is the end of the stream. Hope you have enjoyed it. I enjoyed it, and we are just a little closer to our goal. Thank you for watching. We have advanced one step further.